Welcome everybody. Here we are going to see about the vapor compression refrigeration cycle and with the subcooling effect by kabilan. Here we are in lockdown, cannot go to the colleges and cannot see our friends. All are in stresses. We all miss that colleges and our friends, right? So I created just impact like black and board classes. It will create a little comfort. If you don't get it, it's your fault. Okay, let us make our topic today. We are going to see vapor compression refrigeration cycle with subcooling effect on the contents of vapor compression refrigeration, thermodynamical analysis, vapor compression cycle with subcooling, effects of subcooling, and lastly the applications. Vapor compression refrigerant. What it means? Vapor compression uses a circulating liquid refrigerant as a medium which absorbs and removes heat from the spaces to be cooled, subsequently rejects the heat elsewhere. Where it absorbs, where it removes, is a little confusion, is it? Don't get confusions. We will see it later. And how it do it, man? A little with setups, a compressor, a condenser, a thermal expansion valve called a throttle valve, and lastly a evaporator. Here is the setup. You can see the picture tells you the fact. Yes, here phase transition happens. You can see the vapor goes into a compressor and commit as a vapor and to the condenser to the liquid to the expansion valve, and it produces a liquid plus vapor to the evaporator and then again a vapor to the compressor. And here the PV diagram, you can clearly see a liquid and vapor with a critical point where it is compressed and condensed and throttled and then evaporated. We can see it clearly as step by step on the points. First of all, circulating refrigerant enters into the compressor as a thermodynamic state called a saturated vapor. You all know the saturated vapor, yeah? Yeah, it means a vapor in the point where it is heated, it goes to the superheated vapor. Literally means you need a latent heat to make it as a superheat vapor. Then in a compressor, it compresses to the high pressure. Also, it means if it's a high pressure, it will go to increase in the temperature. Literally, as a if pressure increases, the subatomic distance between the atoms will be reduced, and processly it goes to higher increase in temperature. So it made up to the superheated vapor. It can be condensed with either cooling water or cooling air flowing across the coil or tube, and refrigeration reflects the heat from the system. You know where it rejects the heat, of course, to the surroundings. Yeah. And then the saturated liquid. Yeah. After condenser, it will become a saturated liquid. Here, the phase transition occurs at the critical point. So, saturated liquid is next routed through the expansion valve where it undergoes abrupt reduction in the pressure. So, reduction in pressure means a reduction in temperature. It lot of losses in temperature here. So, the pressure reduction results in adiabatic plus evaporation. What it means, man? What adiabatic means, it's a constant entropy, and plus evaporation means a partial evaporation. So here the liquid converted into the mixture of liquid plus vapor. So the auto refrigeration effect of the adiabatic flash evaporation lowers the temperature of the liquid and vapor refrigeration mixture to where it's colder than the temperature of the enclosed space to be refrigerated. So this point explains clearly what the refrigeration means. So the auto refrigeration, the effect of the adiabatic flash evaporation lower the temperature of liquid and vapor refrigeration. So literally we can say the temperature of the fridge is higher than the temperature of the refrigerant. So in from the higher concentration to lower concentration, this theory explains it. So the temperature, even in the lower temperature, it passes some amount of heat to the refrigerant where the refrigerant loses that heat on the condenser to the surrounding. So this is how refrigerant works. A fan circulates the warm air into the enclosed space across the coil, and the warm air evaporates the liquid part of the cold refrigerant. So evaporator uses a fan-like machine to heat this evaporator. So the evaporator heats up the liquid and vapor refrigerant, so it converted into the clear vapor again. A vapor is where a circulating refrigerant absorbs the heat and removes the heat, which subsequently reject the condenser and transfer elsewhere by the water or air. Complete refrigeration cycle. So here it happens. So now we are going to analyze this like a thermodynamically. You can see the temperature and specific entropy graph. So you can see clearly the saturated vapor converted into the superheated vapor to the saturated liquid and again to the vapor plus liquid mixture, and to complete the cycle it again converted into the saturated vapor. 1 to 2 it's a compression of vapor, and 2 to 3 vapor superheated removed in condenser, and 3 to 4 a vapor converted into the liquid in a condenser, and 4 to 5 here the flash transition occurs in the expansion wall, and 5 to 1 the liquid plus vapor converted into all vapor. So the point explained here. 1 to 2 isentropically compressed, that means constant entropy, and exists a compressor as a superheated vapor. And point 2 to 3 a vapor travels through the part condenser, which removes the superheat by cooling the vapor, and 3 to 4 a vapor travels through the remainder of the condenser and is condensed into the saturated liquid. So between the 4 to 5 the saturated liquid refrigerant passes through the expansion wall and undergoes abrupt decrease in pressure. Again the adiabatic flash evaporation takes place, and in between the point 5 and 1 cold and partially vaporized refrigeration travels through the coil and tubes in the evaporator, where it totally vaporized by the warm air that fan circulates across the coil. Evaporator operates essentially constant pressure and boil all the available liquid, thereafter adding 4 to 8 kelvins of superheat to the refrigeration in order to make sure the liquid has evaporated completely. This safeguards the compressor. It cannot pump the liquid. The resulting refrigeration vapor returns to the compressor inlet at the point 1 to complete the thermodynamic cycle. Don't get any little confusion. Here the evaporator does additional work. What the additional work is, in compressor, if the the vapor is not saturated, if it's not a saturated liquid, it has to we have to give a more work to compress it to the superheated vapor. So here the evaporator does additional work to reduce our work by adding a 4 to 8 Kelvin of heat to the vapor. Already it makes a superheat likely. The above discussion is based on the ideal vapor compression. Yeah, of course, there is a refrigerant cycle which does not happen in the real world like this because of the frictional pressures and additional mechanical defects. So always this theory make up by the ideal vapor compression. So what with the subcooling, man? Also with the subcooling, it happens a superheating, but with the superheating, it doesn't matter the more effectiveness. Uh, the effectiveness lies in the subcooling, man. So what is subcooling? It's nothing but the subcooling means if we have to say openly, what is the impact of the subcooling? The reduction of the superheated vapor, that's what. The loss of the heat to the surrounding is improved with the subcooling. So the condenser passed by a tube with a cooling fluid inlet and absorb the heat and get the output as a cooling fluid out. So it reduce the temperature of the condenser and improve the heat losses. Okay. So we can see it up in the theory clearly. So here the TS diagram, the entropy and temperature diagram, you can see clearly at the output of the condenser, the heat is reduced to the 3 dash. Okay, if it's in 4 dash and 4 double dash, you can see the absorption of the heat from evaporator increased if we do a subcooling. In actual refrigeration cycle, the temperature of the heat sink will be several degrees low than the condensing temperature to facilitate the heat transfer. So this point clearly explains what happening. The actual refrigeration cycle, the temperature of the heat sink will be several degrees lower than the condensing temperature to facilitate the heat transfer. Hence, it is possible to cool the refrigeration liquid in the condenser to few degrees lower than the condensing temperature by adding extra area for the heat transfer. In such cases, the existing condition of the condenser will be in the subcooled liquid region. Hence, the process is known as subcooling. So, it's nothing but the condenser in the subcooled region. So, the condensing fluid temperature is loses the more heat in the subcooling condition. Ultimate aim of the subcooling is to increase the coefficient performance under the same set of conditions. So what is the effect of subcooling? Here the COP calculation. In a normal COP calculation, it always do the rejection of the heat is H1 minus H4, and now it is equal to H1 minus HF3, the subcooled enthalpy. So H4 is equal to H3 HF3. So how we can calculate HF3? HF3 is nothing but equal to the HF3 dash minus CP into degree of undercooling. So here the COP equal to refrigerating effect divided by work done equal to H1 minus H3F divided by H2 minus H1. And the application. Why we doing this subcooling now? So to boosting and economizing the refrigeration effect. An internal heat exchanger is good and relatively cheap solution for the maximization of the heat and exchanging capacity. So subcooling occurs in the condenser to product the expansion valve device. So we can also clearly understand why the subcooling is using. So this is a very small topic, and you can understand why we are using this subcooling technique. And if you want to know more and know more exact points, refer Kurmi book, and we all know whatever book we have to need. So thank you and best of luck.